Welcome back to ChemExam Explained, where the aim is chemistry clarity exam mastery. In today's video, we will be looking at CAPE Chemistry Unit 2, 2021, Module 1. Let's go. Module 1, the chemistry of carbon compounds. 1A, Part 1. Define the term structural isomerism. Structural isomerism is the existence of compounds with the same molecular formula but different structural formulae. Part 2. Identify two types of structural isomers, giving an example of each. 1. Chain isomer. This is where we will move around the carbon skeleton. The example I have here is butane. So let's start with that. Butane would be 1, 2, 3, 4, and 10 H's. The formula would be C4H10 because it follows the general formula CnH2n plus 2. So 2 4 is 8, 2 times 4 is 8 plus 2 is 10. So I should have 10 hydrogen atoms. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now, the other isomer that matches C4H10 would be 1, 2, 3, and I change one of my carbon atoms to become a branch. So now I have 3 as my parent and 1 carbon is my branch. Now I must have 4 carbons and 10 H's. So let's check. 1, 2, 3, 4 carbons, where this is my branch of my parent, which is propane. So this becomes 2 methyl, okay, it's a methyl group, 2 methyl propane. So I have 1, 2, 3, 4 carbons, and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 H's as my parent, and 1 carbon is my branch. Now I must have 4 carbons and 10 H's. So let's check. 1, 2, 3, 4 carbons, where this is my branch of my parent, which is propane. So this becomes 2 methyl, okay, it's a methyl group, 2 methyl propane. So I have 1, 2, 3, 4 carbons, and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 H's. So here we have our 2 isomers for C4H10. A positional isomer would be for type 2, where I could use an alkene. And let's go with CnH2n. So that alkene, let's go again with 4 carbons. So that's C4. 2 times 4 is 8. So I have 1, 2, 3, 4, and that's my double bond there. Each carbon must have 4 bonds. So 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, and 1, 2, 3, 4. So this is but1-ene. The other isomer must be but2-ene, where I change the position of the carbon-carbon double bond. So it was between the first and second carbon. I will now move it between the second and third carbon. So that's 1, 2, 3, and 4. So let's put in our H's, and we must have 4 bonds around each carbon. So here I have but1-ene, and this is but2-ene. Now the question asks for 2 types, but let's go with a third type. And the third type could be a functional group isomer, where we are going to change the functional group of our molecule to another functional group. So in this case, we can start with propanol. So that's 1, 2, 3 carbonyl group with a H, and that is our propanol. And the isomer, which is a structural isomer, would be propanone. Now, you move between an aldehyde and a ketone for this type of isomers. Let's put on our H's. Now, notice we must have the general formula. In this case, I must have C, which is 1, 2, 3. So 3 carbons. 1, 2, 3, 4, 5, 6 H's, and 1 O. Both should have the same formula. So that's 1, 2, 3, 1, 2, 3, 4, 5, 6, and 1 O. Part B. A gaseous hydrocarbon P of volume 10 cm cube of the formula CXHY was mixed with 70 cm cube of oxygen and exploded in a reaction chamber. After cooling to room temperature, the gaseous mixture occupied a volume of 55 cm cube. After shaking with aqueous sodium hydroxide, the volume was reduced to 35 cm cube. The remaining gas was shown to be oxygen. Now, all volumes were measured at constant pressure. The following equation represents the combustion of P with oxygen. So here is our equation that we're going to use to solve the problem. Let us first identify some important values. Here we have the volume of hydrocarbon. So the volume of the hydrocarbon P is 10 cm cube. That's the first thing. The next thing you notice is that they said that the hydrocarbon was mixed with 70 cm cube of oxygen and exploded. So there's a reaction taking place now. Now, after cooling to room temperature, the gaseous mixture occupied a volume of 55 cm cube. So we call that residual gas. So the residual gases include excess oxygen and carbon dioxide. So let's see how we can find out what is the excess oxygen and what is the value for the carbon dioxide. After shaking with aqueous sodium hydroxide, the volume was reduced to 35. So this is the key. Sodium hydroxide or potassium hydroxide will absorb carbon dioxide. So after they pass the residual gas through the sodium hydroxide, it was reduced to 35. So we saw that the residual gas was 55. It was reduced to 35. So we could use those values to find the volume of carbon dioxide. So that would be the residual gas, which is 55 minus 35 equal 20. So the 20 here is the volume of carbon dioxide produced. So if we said that the residual gases included excess oxygen and carbon dioxide, and 20 cm cube was carbon dioxide, then 35 would be your excess oxygen. So anything on this side is being used up, anything on this side is being produced. So we know that 20 cm cube of carbon dioxide was produced, and we need to find the amount of oxygen used up. So the volume of oxygen used will be the volume of oxygen given in the question to be 70 minus excess oxygen, which we calculated to be 35. So the volume of oxygen used would be 70 minus 35 equal 35 cm cube. Now we're going to carry out our calculation using the empirical formula method. So when we put 10 cm cube for the hydrocarbon, 35 cm cube for the oxygen, and 20 cm cube for carbon dioxide, we must divide through by the smallest value. So it's 10 divided by 10, which is 1, 35 divided by 10, which is 3.5, 20 divided by 10, which is 2. So any value we get here for carbon dioxide is the number of carbons present in carbon dioxide. So right away, we know that X is equal to 2, which represent the number of carbon in our hydrocarbon, CXHY. So from the formula, x plus y over 4 equal this value right here. And we know that x is equal to 2. So we can now solve for y. So 2 plus y over 4 equals 3.5. Y over 4 equals 3.5 minus 2. Y over 4 equals 1.5. Y is equal to 1.5 times 4. Therefore, y is equal to 6. From that, we can deduce our formula because x is equal to 2 and y is equal to 6. So in looking at CXHY, we get C2H6. We can now write a fully balanced equation. So C2H6 plus oxygen give us 2 carbon dioxide, which we know, and 3 H2O. How did we get this 3 right here? Because y is equal to 6. And here we have 6 divided by 2 equals 3. We know that x was equal to 2, so therefore 2 carbon dioxide. Once we have those values, we can now balance carbon. So here we have 2 carbon, 2 carbons. We have 3 times 2 H's, which is equal to 6. We have 6 H's here. We can now balance the oxygen. So 2 times 2 equals 4, plus 3 equals 7. What we do, we now must find a value that when you multiply by 2, you get 7. And that value would be 3.5, which is the same thing as 7 over 2. B part 2. Write the displayed structural formula of P. So we know that P is C2H6. So all we do now is we write out the displayed formula for the alkane. Part 3. Outline the reaction mechanism for the reaction of P with liquid bromine using appropriate notations and equations. So we know that this particular mechanism, when working with alkanes and halogen in the presence of UV light, is free radical substitution. We have 3 parts to it. We have initiation, we have chain propagation, and we have termination. In the initiation stage, we need UV light to break the bonds between the halogen atoms. In this case, the bonds between bromine and bromine. We now produce what is called radicals. Radicals are species with unpaired electrons, and they are very reactive. So without creating the radicals, the reaction cannot proceed. That is why it is called initiation. Now for part 2, we have chain propagation. Chain propagation is 2 things will happen in chain propagation. Firstly, the free radical that you produce, you are going to use it to form an alkyl radical. Then the alkyl radical will react with more halogen, being that the alkyl radical is now the reactive species. So in chain propagation, we must show how we move electrons around. If you come back to initiation, you see that we have a bond here. A bond represents 2 electrons. So let's represent the bond with 2 electrons. So here we have Br, and we have our 2 electrons. We are going to use curved arrows to show how we move electrons. Now, if I am moving these 2 electrons, I must use the double barbed arrows. Now, what will I produce here? I will produce ions because the Br here is positive because the electrons are all gone here. And now I produce Br minus where the electrons are on it. But we are not doing heterolytic fission. We're doing homolytic fission. So let's write back our Br. And now I am moving 1 electron towards Br and another towards that BR. So notice the single barbed arrow is moving only one electron. So we move one electron towards this BR and one towards this BR. We create free radicals. Our free radicals are very reactive. So it will start the reaction in our chain propagation. So once we have the free radical, Br radical will now combine with one electron from this CH bond. The other electron will move towards the carbon, hence forming an alkyl radical. These two electrons that join will form the bond between H and Br. We now have a very reactive species, which is the alkyl radical. That alkyl radical will now react with more halogen, which is, in this case, bromine. So the alkyl radical, the electron from the alkyl radical, will bond with one electron from the Br-Br bond, and the other electron will go onto Br to form another radical. So the Br radical was regenerated. Now, this radical would continue to remove more H's, but we're going to stop it by terminating all free radicals from the reaction. So these are all the possible ways you can terminate the free radicals. You could join Br radical with Br radical. Those two electrons would form one bond. We now have Br. You could join a Br radical with the alkyl radical, and you bring them together to form a C-Br bond, and you eliminate these radicals. You could join two alkyl groups that are free radicals. So these two free radicals would join together by forming a pair, and now we have a bond here. So that's how we removed our free radicals, preventing further reaction from taking place. Part 4. Identify the type of reaction mechanism outlined in B, part 3 on page 5. We did say that the mechanism outlined was free radical substitution. Part C. Compound Q is an acyclic hydrocarbon of molecular formula C4H8. Part 1. Write the displayed structural formula of two isomers of Q. Now, looking at the formula, we see that C4H8 would give us an alkene. So we could draw our structure for our first isomer as but1-ene, where we put the double bond between the first and second carbon. In our second isomer, the double bond would move from between the first and second carbon to the second and third carbon, and this would represent our two isomers. Part 2. State whether compound Q exhibits geometric cis-trans isomerism. Well, we say yes, and in this case, it is but2-ene that exists as geometric isomerism, not but1-ene. Why? Because for you to exist as a geometric isomer, aka cis-trans isomer, you must have two identical groups attached to adjacent carbon atoms. So here we have H attached to this carbon, and this is the adjacent carbon, and we have another H here, or we have a CH3 group attached to this carbon, and the other adjacent carbon also have a CH3 attached to it. So the reason why it exhibits geometric isomerism, we have two reasons. The first one is because we have identical groups attached to adjacent carbon atoms in the carbon-carbon double bond. Secondly, we must have different groups attached to individual carbon atoms. So this carbon will have a H here and a CH3 here. Once we have that, then we know that it will exhibit geometric isomerism. If we had two H's on this carbon, then it would not exist as geometric isomerism. Now, when you have the two same groups on the same side of the carbon-carbon double bond, we say that it is cis. So the name in this case would be cis-but-2-ene. And here, when you have the two same groups on opposite sides of the carbon-carbon double bond, we say it is trans, for transverse. So the name would be trans-but-2-ene. Part 4. Outline the mechanism for the reaction between compound Q and HBr using curved arrows to show the movement of electrons. Remember earlier, we say that once you're looking at the movement of electrons, we use curved arrows. But the single barbed arrow move only one electron, while the double barbed arrow or curved arrow move two electrons. So in this case, we are not moving one electron, we are moving two electrons. So to do this mechanism, we must draw out our structure. Now we could use but-2-ene as well as but-1-ene. We're using but-1-ene in this case for us to look at the Markovnikov rule. If we use but-2-ene, then the H and the Br can go on either carbons, does not matter. In this case, with but-1-ene, we have a carbon with two H's and a carbon with one H. So when we add HBr, according to Markovnikov rule, the H from the HBr must go on the carbon with a higher number of H's, while the Br will go on the carbon that is more stable. That is the one with a fewer number of H's. So let's look at what's going on here. As HBr approaches the highly rich electron density in the carbon-carbon double bond, we have an induced dipole taking place here. Now, when I say induced dipole, what is happening is that our H and Br will become partially charged. So since electrons don't want to be beside electrons, these electrons here will move away from the H and move towards the Br, making it partially negative. The H will become partially positive. Hence, we have what is called an induced dipole. Now we have our induced dipole. The electrons from the carbon-carbon double bond can now bond to this H, forming an H bond right here. Now, if we move two electrons from the double bond, then this carbon will no longer be satisfied with the number of electrons it needs. So it will now form a carbocation, which is a carbon with a single positive charge. So as this bond to the H, this will break off and Br will come by itself here. Now this is your bromide ion. Now this is a negative ion because it now has two electrons that broke off from the bond between the H and the Br. Now the negative will move towards the positive carbocation to form a C-Br bond. And that would complete our mechanism by reacting compound Q. In this case, we use the isomer but-1-ene to form our bromoalkane. Part 5. State the type of reaction mechanism outlined in C, Part 4. And we said that earlier, that reaction mechanism is electrophilic addition. Remember that in this case, the HBr would have a partially positive H and a partially negative Br. And this would act as our electrophile. Part D. Describe the observations expected for each of the following reactions. D part 1. Aqueous bromine is added to liquid pentane in sunlight. Now, the in sunlight is very important because if you are reacting a halogen with an alkane in the presence of sunlight, then that is our free radical substitution mechanism. Okay, so what that would mean is that when we react our bromine with pentane, we are going to substitute a H with a Br. And that would cause the brown bromine to become colorless. What am I saying here? If my pentane is 1, 2, 3, 4, 5, I have all my H's on my pentane. I'm going to react that with bromine, liquid. So it simply means that I'm going to substitute a Br with a H, and that H would combine with the other Br. So what will I get over here? I'll get 1, 2, 3, 4, 5. This one would have been substituted with a Br, and these are all H's. Plus HBr. So this here would be brown, and when it reacts, it becomes colorless. And that is why we get now the observation from brown to colorless. Part 2. Aqueous bromine is added to liquid pentane without sunlight. Now notice this time we're not using Br2 liquid, but Br2 aqueous, which is also brown. However, we would have no reaction taking place. And if we have no reaction, then we have no color change from brown to colorless. Or you could say no discolorization. Why not? Because we don't have any sunlight to initiate our reaction, which cause the splitting of the halogen. So without sunlight, you have no reaction because our reaction is with an alkane. If it was an alkene, you don't require the use of sunlight because the alkene is already reactive. So once you're looking at an alkane, you need sunlight to have any substitution taking place. Part 3. Cold acidified potassium permanganate solution is added to liquid pentane. Now, the first thing I want to say is that the potassium permanganate is an oxidizing agent, represented by an O in a square bracket. Now, the oxidizing agent would not react because the pentane, being an alkane, would not cause any substitution to take place on the pentane. However, if it was an alkene, it would be a reducing agent, reducing the potassium permanganate from purple to colorless. But because our pentane is not an alkene, it is an alkane, we would have no color change with the potassium permanganate solution. Or you could say the solution remained purple or no discolorization. This is the end of Module 1, 2021, Unit 2. Please remember to like, subscribe, and click the notification bell so that when new videos are uploaded, you will be notified. Thank you.